So last class we introduced this concept of what's called the group orbital approach for determining the molecular orbitals of a molecule. And in this process, you take whatever your outside atoms' orbitals are and you group them together according to the rules of symmetry, and then you develop the reducible representation for how that group transforms under the symmetry operations of the point group defining the molecule. And then you break that down, or you reduce it, and find what symmetries are present in that reducible representation that match the atomic orbitals of the central atom. And that defines what's best, okay, what's best going to bond together, all right? Today we're gonna extend that, go a little deeper into that, do it some more, and then we're going to look at a different system. It's almost like a shortcut, but I don't want you to confuse it as a shortcut. So group orbital approach looks from the outside to the inside. And then there's another method where you look from the inside out, where you start with the central atom, okay? And you make an assumption. This atom must obviously be bonded to all the stuff on the outside. So how is the central atom using its atomic orbitals? What orbitals must it be using to bring that bonding about? All right? And so that's the sort of the second way that we're going to approach this. Okay. What I'd like to do this morning is maybe another application. Let's do. We did in class last time. I think we worked through the group orbital approach for carbon dioxide. If I'm correct, is that what you guys have in your notes? But we didn't necessarily do it for water or for ammonia or something like that? No? Okay. All right. Okay. Let's look at the ammonia case. Let's look at the NH3 case. And let's see if we can develop basically the MO. It's not going to be the MO diagram, but the MO, let's call it the MO matching. Okay? All right. Using the group orbital approach. Okay. So our ammonia molecule, right, is going to be in the C3V point group. Okay. That's where we would need to start any analysis. Is knowing what point group the molecule is in. All right? And so then this is going to define, this C3 axis is also going to define what is Z in this molecule. Okay? And every other atom, the hydrogens in particular, have to abide by that same Z axis. What can be different, though, on the hydrogens is that their Y axes point towards the nitrogen. Okay, so each hydrogen's Y is actually not coincident with the other hydrogen Y, right? Because one is pointing this way as Y, another one's kind of pointing at a different angle in at Y. All right, but it's all relative, and then X would be perpendicular to that. All right, although that's not going to be really important, as it turns out, because hydrogens have only one s orbitals. So a different way to look at this would be, here's our nitrogen looking right. I'm looking down this from the top. We'd have one hydrogen there, and one hydrogen there. Okay? And so this molecule has the C3 axis right here. Okay? And these are the three 1s orbitals of hydrogen. So now we'd like to look at the point group and develop the reducible representation. So bring up our C3V point group. There are only three operations. E 2 C3s, and 3 sigma Vs. So we'd like to develop the reducible representation for the group of 1s orbitals that we have here. Okay. So there are 3 orbitals. When we perform E, all 3 of them are unchanged. None of them move. So the character is 3. Right? When we perform a C3 operation, they all move. They move to the position of another one. But in this analysis, anything that moves, remember, contributes 0 to the character. So all of them move, so there's nothing there. And then the sigma V's would all be a plane like that, going down vertically through this. So these 2 would move, but this one would not. So it's going to have a character of 1. Okay, so that's our total reducible representation describing this group here. Any questions on that so far? That's back from chapter 4, but slightly different because we're not doing it with our 3 vectors now. We're just doing it with the lobe, and the sign didn't change here. That's why there's no negative ones or anything. If you had a p orbital, okay, if we don't need to, but if we had a p orbital that was on here like this, when we performed the sigma v, this one would flip sign, okay, so it would contribute -1 in that case. All right, that would be the only way you could get that. Okay, all right. So now we need to look at the rest of the character table. There are 3 irreducible representations in this point group: A1, A2, and E. Okay, they are 1, 1, 1. 1, 1, minus 1, and 2, minus 1, 0. What we need to do now is figure out in this gamma, this reducible representation, how many of each of these are present. Okay? And by inspection, I can kind of, if you do enough of these, and I hope someday you can say this for yourself, I could see it's going to be an A1 plus an E. There's my 3, there's my 0, there's my 1, right, when I add them together. Right, this is a relatively simple one with just a few to choose from, okay? I don't expect you to be there yet, right? I said someday with enough practice, you'll be there, okay? All right, but how would we prove this? So how many A1s are in here? 1 over 6. Why 6? 6 is the order of this group. 1 plus 2 plus 3. The sum of the coefficients of the different classes is the order. So 1/6 of. Now we take coefficient of the class times the gamma value times the A1 value. So 1 times 3 times 1, so that's 3, plus 2 times 0, 0, plus 3 times 1 is 3. So 6 divided by 6, there's going to be 1 A1 in gamma. A2. 1/6 of 3 plus 0 minus 3, because the last value is -1. That's 0. And n of E, 1/6 of 1 times 3 times 2, so that's 6, plus 0, because E has a 0 in the C sigma V column. So that's still 1/6 of 6, so it's 1. So gamma equals A1 plus E. So what this means, guys, is this is describing the symmetry of this group of 3 hydrogen 1s orbitals. Okay? It's sort of a collection of their symmetry. Now, out in the right, I've unfortunately chosen to write in the WRITE. I've chosen to write in the incorrect spot here, because in this part of the character table is the next bit of information that we need. I'm going to write it out to the left, though, but usually it's out there on the right side. So next to A1 is the letter Z, and then even further out, well, we don't need that actually anymore. And then down here next to the letter E is X, Y. These are indicating the orbitals, the symmetries of the orbitals, okay, of a central atom in any molecule in this point group. Okay? All right? And what's missing, what's not written, what's implied is that S is always A1, but it's not written. That's like that's an yes, because it's always symmetric. An S orbital is symmetric, right? That matches the A1 or the AG, whatever. The first row is always the all symmetric row. Okay? So, what we can do then is we can say, well, okay, the nitrogen, this would be the second row, or second period, right? The nitrogen 2s has A1 symmetry. The nitrogen 2pz has A1 symmetry. And the nitrogen 2px and 2py have E symmetry. Okay. So the symmetries of the nitrogen orbitals, we're looking for matches between those and the group that we just looked at. And we see pretty good matching here. Okay? So the nitrogen, now we get into sort of a more detailed analysis. The nitrogen 2s, okay, could bond with the H group because the 2s has A1 symmetry, the group has A1 symmetry. The nitrogen 2pz, again, could bond with the H group. And the 2px and 2py also can bond with the group. Okay? So the question then becomes, all of the nitrogen orbitals have symmetry matches. So the next question is, which matches are best energetically? Right? There's the two parts of the two big conditions of MO matching up is not only the symmetry but the energy. So we find those energies back in this table in our text. Where'd that come from? There it is. Page 134 is where I'm finding it. Okay. So the nitrogen 2s is negative 25.56 electron volts. The hydrogen 1s, which would apply to the hydrogen group, they're all hydrogen 1s's, are negative 13.61. The nitrogen 2p, which would define the 2pz and the 2px and 2py, they're all going to be the same. Nitrogen 2p's are negative 13.18 electron volts. So we actually see that the strongest interactions between nitrogen and the hydrogen group will be the 2px, 2py, and 2pz with the hydrogen 1s orbitals. Okay. The 2s is in the realm of possibility. Okay, it's inside this rough 15 electron volt gap. That outside of that 15 electron volts, the interactions are really too small to consider any significant bonding character. But this really close match here says that the stronger interaction is going to come from the 2px, 2py, 2pz. Now, there's one small problem with that. If we visualize these orbitals, okay, of our nitrogen, here's our 2s essentially, right? there's our 2pz. Okay. Our nitrogen X and Y get out of the way. Yeah. So if we're imagining the hydrogen groups and where they're placed, according to the point group and the z-axis, it actually seems like the 2pz should really not be used for any bonding. It's most likely where the lone pair of electrons is going to be stored, okay, which is kind of goes against what we just showed in terms of energy, match, the better energy match here. So there's limits to this, in other words, this qualitative approach that we're using. And then there's a much more quantitative approach described right after this in the text, okay? But again, I'm not going to step on your PChem toes, so to speak, all right? And you'll learn how computational tools really can make these decisions for us. Okay, but you need to understand what you're asking the Gaussian program to do. For those of you who've used Gaussian, right? So I'm not wrong. We have a couple students who have taken our PChem, right? And when you construct and ask a molecule or ask Gaussian to construct the energies, you do need to provide the symmetry of the molecule in a lot of cases, or does that sound familiar? Or maybe it depends on what you've done, what you're doing exactly. But I can remember having to specify that for a couple calculations that Dr. Forsman helped me run. So, okay. All right. Okay. Any questions as we go through that? Okay. So let's look at, I'm going to give you a head start on one of the homework problems that I'm going to be assigning for you today. But because it's a little more involved, let me just make sure it's the right one. Yep. So for 520, the molecule in 520 is SO3. The wording is written horribly, I think, in the problem, for at least for what I want you to do. I'd like you to do SO3, but I'd like you to use the group orbital approach, just like we did here for NH3, to determine the best matches between B/N, between sulfur and the oxygen group. Okay? So sulfur trioxide would be a planar molecule. Okay? SO3, there'd be some resonance going on there, which doesn't affect the symmetry. And so it's in a different point group because it's planar. It is, I believe it is the D3H point group, just like the one on the back of your homework that was due, that you handed in today, I think, right? Was a D3H. Yeah, so BH3. So in your homework, I'd ask you to look at BH3, which just has the s orbitals, like we just did for ammonia. So what's different now is we're building up. Now you're going to have S and then the P, X, P, Y, P, Z. Okay? But let's get all on the same page. Our C3 axis is going to be right there. Okay, so we're looking down the C3 axis, just like we oriented ammonia over there, looking at it from above. Okay, there's this C3 axis here. Okay, so as part of the D3H point group, we're going to have 4 groups, because each of these oxygens has an s orbital, and then there is a pz, a px, and a py. The z's would be coming out of the board towards us, okay? And then the y would be, it's actually easiest to draw the y. These would be the py's in each case. And then the px's would be perpendicular to them like that. Okay? And then again, the Z's are coming out of the board. So we're going to develop a gamma, a reducible representation for the 2s group. And then we'll do it again for the 2p Z group, the 2p X group, oops, and the 2p Y group. Okay. All right. So the D3H point group. Where'd you go, D3H? There we go. We've got an E, 2 C3s. We have 3 perpendicular C2s. We have sigma H. And then we have the 2 S3s, improper rotation reflections, and 3 sigma Vs. Okay. All right. So the S's, again, we want to picture 3 S orbitals, okay, centered around our sulfur. And now we want to see how that changes as we operate in each of these cases. 3, no change, right? Sigma 3, or C3, 0. They all move. C2, the C2 axes are right through an SO bond. So these two would move, and this would not change at all. So that would be 1. Okay? Sigma H is the plane of the molecule. So all 3 stay the same, and they don't change signs or anything. So it's 3. S3 is a rotation. So we're done. As soon as they all move, we know it's 0. Okay? So that makes it easy for us. Okay? And then sigma V is a vertical mirror plane, just like through that C2 axis, just like it was for ammonia in the previous example. Okay, this would be a vertical mirror plane, so only one of our things would change. 301, 301. Okay? How are we doing? We getting these? Getting these okay? All right. Now the 2PZs, a little hard. Again, this is coming up out of the board and back into the board. Okay? So again, when we do E, we know nothing changes. Okay? When we do sigma or C3, they all move again, so that's going to be 0. It's going to be a pretty common theme, I believe. When we do a C2, so now let's focus on the oxygen at the top here. When we do a C2, these two move, so they contribute 0. What about the guy at the top? His top lobe, say it was positive, gets flipped around to back behind the board, and so the negative is brought out to the front. So that character is -1, right? For sigma H, the plane of the board, we're just going to flip the front half at the back. So now all of the front halves, if they were all positive, are at the back. All the negatives are at the front. All of them are negative, right? Each of those is contributing a -1. S, again, we've moved it, so the character is going to be 0. And the sigma V, the vertical mirror plane, these two would move, and the PZ would be unaffected, all right? Because now we're not flipping it top to bottom, we're flipping it left to right. And so the signs don't change there. So 3, 0, -1, -3, 0, 1 is our character here. PX. So now we've got 3 of these X ones that are like that, perpendicular to each of the bonds. Okay? And again, they're shaded. 1/2, doesn't matter which, but 1/2 is shaded. So when we perform E, no change. C3, they all move. C2. Now we do a C2. Again, I'm just going to continue to use this as my C2 axis, right? So these bottom ones move. What happens to this? Its signs change, right? And so that means it's also a -1. Now sigma H. These PXs are in the plane of the board. So they're reflected right onto themselves, the top half to the bottom half, and they're not crossing the node, right? So they're staying unchanged. So that's a 3, positive 3. Everything moves on S. And now sigma V, now our sigma V is going to flip the left and the right sides of our PX. So it's going to be -1. 3, 0, -1, 3, 0, -1. Okay. PY. Okay. All right. 3. Okay. So here's our PYs. Okay, I guess I can draw them all in for us. Okay, again with the shadings. Okay. None of them change on E. They all move on C3. On the C2 axis, continuing to use the same C2, now this PY is just like a hot dog on a spit. It doesn't change at all, okay? Because you're rotating it right along that axis. So the positive end that I have pointing into the sulfur is still pointing in, the negative end out. So that's a positive 1. So 3, 0, 1. Sigma H, well again, these are in that plane, just like the X's were. So they're a positive 3. They all move on S3. And now sigma V bisects that orbital, so just the left side switches to the right side, but the signs stay the same. So it's 3, 0, 1. Okay. All right. So here's your head start. So now you're going to do what we did, so you're halfway home, so to speak, for this problem. So now you'll need to do the reductions, okay, just like we did here. So there's 4, you'll have to reduce, it's a lot, it's a fair amount, so that's why if you can, sort of start to figure out which ones are which. Although notice that these two are identical. So once you reduce gamma for 2S, you've reduced gamma for 2PZ. Please don't redo it, okay? Obviously, they're the same, okay? So that saves you a little bit of work, but you need to reduce each of these, okay? And then once you've gotten them reduced, you're going to look in these right-hand columns for the orbitals of sulfur that provide the best match. Sulfur, as a third period element, has not only its S and P orbitals available for bonding, it has D orbitals available for bonding as well. And so you have to look at not just the first column, but the second column where the D orbitals are located to see if there are any matches between the atomic orbitals of sulfur and the groups that you've reduced there. Okay? People clear on what they're doing now for that one? Okay. So the other approach that we can use to develop like an idea of what's going on with the MO structure is to think about the interior, the atom at the middle of the molecule, and to basically borrow from valence bond theory, where in valence bond theory, if you recall, way back from Chem 1, we acknowledged that the bonding in certain molecules doesn't, or the known shape of certain molecules does not match the orientations of our orbitals, right? So, for example, this is, roughly speaking, a carbon atom, the 2s and the 2p orbitals, okay? They're all oriented at right angles, but in CH4, the bond angles we know are at 109.5 degrees, right? So here we've got 90-degree angles between our P's, but here we've got 109.5 degree bond angles, all right? And what we say in Gen Chem 1 is that carbon has been hybridized. right? In this case, we say it's sp3. That the s orbital and the 3p orbitals are mixed up to create a new set of orbitals, all right, that match what we know will be the bond angles of this molecule. And then our hydrogens come in. These are the hydrogen 1s orbitals, these little circles that I drew on the outside, and they'll form overlaps. Okay. Well, that idea of hybridization, in Gen Chem, is strictly speaking belongs to the valence bond theory and to Vesper, right? All the shape stuff. Okay. But it turns out that these hybridizations can be predicted through MO theory and our work with this group orbital approach and group theory as well. Okay, so that's what I want to show you is that we can predict the hybridizations, the probable hybridization schemes hybridization scheme of a central atom using group theory. Okay. So let's do the case of methane, CH4. So to do this, you're going to draw the known shape of a molecule with arrows or vectors, okay, pointing from the central atom to where the exterior atoms are. Okay. So in methane, that would then be this right here. This one technically would be coming out of the board. This one would be back to the board. We don't necessarily use the wedge and the dash like we do in other cases. All right? And so I'm not actually drawing in the hydrogens. Okay? These arrows represent the known bonds that we know these four bonds have to exist. So what we're going to do is work backwards and figure out, so how is carbon conspiring to arrive at this, in other words. Okay? And so now we're going to develop a reducible representation. For the set of arrows. Okay. So methane is in the TD point group, tetrahedral point group. The gamma of these four arrows, okay, there are several operations that we have to consider. There are 8 C3 axes. There are 3 perpendicular C2 axes. There are 6 S4 axes and 6 dihedral mirror planes, sigma Ds. Okay. When we, so the rules here again are a little bit different. This is the third time we're going to perform this sort of analysis. One time we did it with an XYZ coordinate, and you had to figure out how each of the coordinates transformed. Earlier today, we were doing it with the group orbitals. How did the signs of the lobes change, or did they move? Now, all you have to consider is this arrow, okay, these arrows. And all these arrows can do, it's even simpler. They can be in the same spot, or they can be moved. The arrows can't be changed for their signs, though, okay? They're not like a p orbital, which can have its sign changed one way or the other. Okay, so this is going to be the narrowest smallest group of symmetries that are present, actually. Yeah. Okay. All right. So none of the arrows move upon the E operation. So the character is 4 there. Okay. On the C3 would be coincident with the one of the CH bonds, right? This would be our C3 axis. Okay. So one of the arrows would not move, and the other 3 would. Okay. C2s are kind of coming in through the bond here. Okay, so that's kind of a C2 axis there. They're tough to visualize in tetrahedrals, but nothing is lining up on that C2. Everything moves, okay, on this C2. Okay, all right, so that's a 0. S4, everything would move when you rotate, or then if you reflect. So you could think first you could rotate 90 degrees. Maybe this one wouldn't move. Okay, this arrow wouldn't move. But then when you reflect, it would. And so it's going to be in a different spot. So S's are going to be 0s. And then the sigma D, the dihedrals, are going to have 2, because they're going to split one of these bonds, but they're going to have the other 2 arrows in them. So like the plane of the board is one of these mirror planes, and only these 2 arrows that are out of that plane are part of it. So 4, 1, 0, 0, 2 would be the reducible representation. Okay, so this reducible representation contains the symmetries that the carbon atomic orbitals must exhibit. So in the last 2 problems, the ammonia and the sulfur dioxide, we didn't get there for the sulfur trioxide, sorry, right? But we understand where we're going with this is to see what our group symmetries are, and then to match that to the atomic orbital symmetries. Now we're just concentrating on the atomic atom that's at the middle. And we're trying to figure out what symmetries are present in its orbitals, because we know it's bonded to these 4 hydrogens. Let's take that for granted, okay? And if it's bonded to those hydrogens, the hydrogens must have something that matches it, okay, somehow or another. Okay, so it's kind of a, yeah, let's just get to the point, so to speak. Okay, so this would need to be reduced. Okay, this one reduces to, I will sort of just show you. This one reduces to the A1 and the T2. A1 is, of course, going to be 1, 1, 1, 1, 1. T2 is 3, 0, minus 1, minus 1, 1. Okay. So this gamma equals A1 plus T2. There are others that to be considered, but to save us a little time right here, we'll just take the shortcut that we're told this reduces to this. We could prove that. So what we want to do now is look at these columns out to the right. There's nothing written in the first column to the right of A1, okay? And in the second column, it says x squared plus y squared plus z squared. Okay. Next to T2, it has x, y, and z in parentheses. And then it has, in the second column, x, z, y, z, x, y. Although I think it lists them in a different order, but yeah, but it has those 3. Okay. So again, these 2 columns are defining, labeling, identifying the symmetry of carbon, because carbon is the central atom, the symmetries of carbon's atomic orbitals. What's missing is S, but we know S is here as part of the A1. Okay. These are the D orbital symmetries. Okay. This one is Nothing. But carbon doesn't have Ds actually, so we really shouldn't even be looking at these right now. But in larger molecules, you would look at these. Okay? All right? All right. So what do we do now? Based on the gamma, okay, equaling A1 plus T2, okay, we need to determine the possible combinations of the orbitals of the central atom. Now in this case there's only one possibility. All right, so the A1 implies S, and the T2 implies the PX, PY, and PZ. All together. They go together because they're in parentheses there. Right? They are degenerate, in other words. They're indistinguishable from one another. So you can't just take one. You have to take all three. Okay? So this is saying that because we have to take something that has A1 symmetry and something that has T2 symmetry, we're taking all of this. All right? So we're going to have sp3 symmetry. Okay? We'll do a different example that shows you how that doesn't work. Okay? Okay. Now, if our central atom in this case was not carbon, but was something in the third period or lower, then we'd have two possible options. Okay? All right? If we were something below carbon, which is just the second period, so it doesn't have the d orbitals, then the A1 would still mean S. The S orbital has to be contributed. But the T2 could mean that the P, X, PY, PZ set is contributed, or the D, XY, D, XZ, D, YZ. Right? Because these orbitals have T2 symmetry as well. Okay? So we would now be looking at two possible hybridization schemes. S with the P set or S with the D set. And it has to be the S because your central atom has to have A1 plus T2 symmetry. So it has to have something with A1 symmetry mixed with something with T2 symmetry. But these are the two possibilities. So we could have sp3 or sd3. Okay? All right? In general, this is probably going to be the better guess because the energy match. The energies are closer together for S and P than they are for S and D. Okay? And just like two atoms that we've been looking at, that the closer their atomic orbitals are, the better the overlap is for them, that same rule applies to a atom and mixing its atomic orbitals. The closer the atomic orbitals are into energy, the easier it is to mix them to form the hybridized set. Okay? The other possibility, the other way you eliminate options, we'll pick a different example so that we see it, is based on the shape of the molecule, literally, the literal shape of the molecule. Any questions so far in this, guys? Don't know where to start because there's, no. Okay.
So right of the table?
Potentially, yes. Potentially would use both columns. Technically, I did not need to use both columns for methane because carbon as a group or period 2 element only has a second energy level, and the d orbitals, remember, don't exist, aren't present until the third energy level. And so that's why I could quickly ignore it for carbon. All right. But if this was silicon right below carbon, SiH4, then potentially silicon could be hybridized SD3 instead of SP3 to bring about the tetrahedral shape. Although the probable hybridization is SP because of the better energy match there. Other questions? Other things?
How do you know SP3 is lower energy than SD3?
So we looked at I've been looking at the energy tables a couple of times, right? They don't list the Ds, but if you look in the back of the book, the appendix has the Ds listed, and you'll see they're even further away from the S's. All right, SPD. So obviously P is going to be between the S and the D, so it's going to be closer to S.
So why would SD3 lower energy for the silicon structure? You were saying silicon.
Oh, I'm sorry. SP3 would be the better choice. Is what I meant. Yeah, SP3 would still be the better choice. Yeah. Okay. Yeah. Okay. It's a possibility SD3, but SP3 would be the better choice.
It's always better.
Yeah. For energy match. Yeah. Okay. All right. Now let's look at. Let's do this again. Another molecule, another point group we've seen. All right. Let's look at. Let's predict the hybridization of boron in BF3. Okay. So boron trifluoride. These would be our 3 bonds. The molecule is D3H again, just like our BH3 and our SO3 that we've looked at. Okay. So what's in the D3H point group again? E2C3, 3C2, sigma H, 2 S3s, and 3 sigma Vs. So the gamma of our little vectors, our bond vectors, our arrows, right? 3 for E. 0 for C3, right? The C3 is sticking out of the board right through the boron atom. C2 would be any one of the bonds, so one of them would be unchanged. Sigma H, plane of the board, all of them are unchanged, so 3. S3, they all move. Sigma V, one of them stays in place just like the C2. 301, 301. Okay, we're good? We're all right with getting that now? Okay, getting a little faster at developing those, hopefully. Okay. Again, this would need to be reduced. Okay, there's lots of ones to consider, but we know how to do that. But this reduces to A1 prime and E prime. Okay. Which have these values, these characters. Okay. Out here next to, in the first column and the second column, nothing written in the first column next to A1. X squared plus y squared, comma, z squared. Not in parentheses, so those are different things. Okay, all right. 2 different combinations or 2 different things that have A1 symmetry. X comma y is in the first column next to E prime, and parentheses x squared minus y squared comma xy. Okay. Again, you want to remember that your S is here, even though it's not written. The S is always going to be your, well, it's your all symmetric. This happens to be my all symmetric. I don't want you to just always write S in whatever your first one is. Maybe your all symmetric's not part of it, okay? But usually it is. Usually S is part of the bonding, okay? Okay. This gamma equals this A1 prime plus E prime. All right, so now we got to play a matchup game. All right, of what are all the possible combinations? Okay, we need to develop combinations that have something of A1 symmetry, A1 prime symmetry, sorry, with something of E1, E prime symmetry. So our A1 prime symmetry operations are the s orbital of boron, so that would really be the 2s orbital of boron, right? And then the 2dz squared. Wait, is boron second? Yeah, boron's second period, so the d doesn't actually exist there. But let's ignore that fact for right now, just to show you how we could get all these possibilities. Okay, and I'll show you how we narrow them down. Okay, and then this is not an orbital. That's something else. It's some linear combination of orbitals. Okay, now, that would be useful for Raman spectroscopy. All right, because linear combinations of these coordinates are Raman active, but it's not an actual orbital of an atom. It's not a d orbital. Okay. All right. Now, what has E symmetry? How do I want to do this? I'm going to write my E prime down here. We have the px and py. Okay. And we have the dx squared minus y squared, comma, dxy. Okay. So we have to take something from the group of A1 with something from the group of E prime. Okay. So we could just do the S with the P. This would give us an sp2 hybridization because there are two p orbitals that are degenerate, right, that share, as a combination, that symmetry. So even though it's only one E you're bringing in, it brings in these two p orbitals. Okay, just like over there, it was the 3p. All three came in together for the carbon. Right? So that's one hybridization scheme. We could mix the S from A1 with the D. That'd be SD2. I could mix the D with the D and have a D3. Okay. Right. That's a D, two more Ds. Or I could mix the D with the two P's and get a P2D. We usually list them S, then P, then D. Okay. So I could have a P2D. So these are the four combinations that are possible. Possible. Right? So now which is the best and which is the most realistic is going to depend on the energy, but also on the shape. Okay? One of the reasons I can eliminate the P2D and the D3 because they use the dz squared orbital. I'm going to draw the molecule flat. Right? And there's our z-axis for everything. How does that dz squared orbital do anything to bond to those fluorines? You see? It's not. Okay? versus the px and the py, which would very much be pointing towards, okay, or much closer towards these fluorine atoms. So the actual geometries that can be considered as well for where these orbitals are known to point into space. Okay, so that's why we can eliminate anything that uses the dz squared from a planar molecule. Okay, that same thing will happen in your sulfur trioxide example that you're doing on your homework. If dz squared shows up, it's useless because it's straight up and down, and you're trying to establish bonding in a flat plane. All right, so it's not going to help you very much. Okay. All right. So then that leaves us with the sp2 and the sd2 options. But just like we had earlier, this is probably going to have the better energy match. So this would be the most probable, okay? Again, in reality, there aren't d orbitals for boron, okay? But if this had been, the next element down or whatever, aluminum has d orbitals, okay? So then the sp would still be the better match, okay? All right, so I can look for those energy values in the appendix here. Let's see, unless it's one of the online appendices. I think it might be.
It's all online.
B is online, yeah.
There's 10 sections, 9 sections.
Okay, all right. So we can't find it in the hardbound version of our books. Okay. Okay. Questions? No. Yes. No. Okay. All right. I'd like to have a quiz next class. All right. On this hybridization stuff and on group orbital approach. Okay. Your homework's going to prepare you well for that you're doing tonight or over the weekend. It's already Thursday. Hip, hip, hooray. I've got 4 problems for you to do out of the book, and I want you to do them in this order. Okay? So this is homework set 5.3. We're going to do problem 518, then problem 533. You're going to jump from 18 to 33 because they both work with molecules of the same shape. Okay? 18 is the group orbital approach. 33 is the hybrid scheme approach that we just did. All right? So you should really be seeing the same answer for those two. Okay? Done for the 2 different ways. So that's why I want you to do them in that order. And then do 534 next, which is the similar approach using the hybridization scheme development that we've just done here, but for a different shape. Okay, and then lastly, go back and finish 520, the SO3 molecule. All right, the way we've already started it. Okay, using the group orbital approach, and you've already got that whole, development of the reducible representations. So you need to reduce them and look at the symmetries that match, okay, to finish that one out. So your answers to these problems, just so you understand, how you're answering and things, okay. Yeah. So the answer to 518 is going to be sort of a suggestion of which orbitals of the central atom, talanthanum, best match the group. Okay? For 33 and 34, you're going to list the hybridization schemes or hybridization options and pick the best one. Okay, just like we did for BF3. Okay, so You want to show me that you can acknowledge and understand what all the possibilities are, and then identify the best one out of that group. Okay, don't just write the single best one and ignore all the other stuff that's there. And then 520, you're gonna, like I said, you're gonna finish the SO3 group analysis, and in the end, you should identify which s orbitals best match each group. Right? There were 4 groups for hydrogen or for oxygens. Sorry, the S, 2pz, 2px, 2py. So for each of those groups, you need to say for the S group, the best match from sulfur is blank. For the pz group, the best match from sulfur is blank. All right, and that's going to be done mostly on symmetry, although you could default to energy if you needed to as well. Okay, and again, we'll have a short quiz next time, a couple of questions on it, on all this group theory stuff. Okay, all right, have a good day. I'll see you next time.